Today we're going to be looking at arithmetic versus geometric sequences and see what shapes they form when they are plotted as dots on a coordinate grid. So we're going to go ahead and start with our arithmetic. And what we're looking for when we look at these sequences is we're looking for patterns that are either adding or subtracting. So we've seen these before. We're looking for tables where we're adding the same number to change our y's, or we're looking at simply a sequence. So here's a sequence, 18, 21, 24. So we look and see what we do to an 18 to turn it into a 21, and a 21 to turn it into a 24. And as you know, we are going to be adding 3. So because this is an adding sequence, it's arithmetic. Now, as you can see, our first term is 18. It's the first number that's there. So we know if we were going to put this in the table, which we'll do in a minute, our x of 1 is going to pair up with our y of 18. So the term number is your x's, and the sequence, the actual number that's a part of the sequence, is your y value. So if we were to graph this, we would graph the ordered pairs 118, 221, 324. So I can see to turn an 18 into a 21, I add 3. Now, this has to be the same pattern every single time. So I need to make sure that the next one and the next one, however many numbers I have, are also adding 3. If it ever changes to something else like adding 4, then it's no longer arithmetic sequence. So I do see that 21 plus 3 is 24. At this point, I can go ahead and continue my pattern and see what the 4th term, 5th term, and 6th term. This is very much like your tile problems that we've done before. 24 plus 3 is 27. 27 plus 3 is 30. And 30 plus 3 is 33. However, if I wanted to know what the 100th term is in this sequence, it would take a really long time. Right now, I only have up through my 6th term. So I want to go ahead and I want to come up with an equation for this sequence so that I can find out what the 100th term is by simply plugging 100 in for x and solving for y. And we've already kind of done this with a tile problem. It's very similar. So we're going to go ahead and take a look at this like we would a table for a tile problem. Now, just like a tile problem, when we're creating our XY table, we always start with the number 0, and that's because the 0 term is going to be a part of our equation, or what we call the explicit equation for the sequence. So we're also going to do terms number 1, 2, and 3, because that's what we already have. So we're going to plot what we already know. We know 1 is 18. We know our second term in the sequence is 21. We know our third is 24. And we can see once again, we're adding 3 to get from one term to the next. Now, to find the 0, we're going to do just what we did for the tile problems. We're going to do the opposite of adding 3, which is subtracting 3. So we know that our 0 period is 15. Now, if we didn't want to transfer that to our table, first of all, that 0, 15 we know is our 0 figure. And so that is our y-intercept. So when we're looking at an equation, that's going to be our b for this. And then, of course, our pattern is our slope, and that is our m. So it's the same like we did with our tile problem. The change or the pattern is the slope, and the 0 figure is our y-intercept. In this case, it's the 0 term. Now, it doesn't really exist. Our term sequence starts with 1. But we can go ahead and work backwards to do the opposite of adding 3 just in our sequence and not transfer it to a table, and do the opposite. 18 minus 3 is 15. So some people like to transfer it to a table. Some people just like to work on the actual sequence itself. That's going to be personal preference. So this, of course, is a line. We know that when we are consistently adding the same number again and again and again, that's our slope, and that's going to form a nice straight line. And we know our lines have the formula y equals mx plus b. In this case, in all cases, we know that m is our slope of our line, which is our pattern in this case. What are we doing to get from one term of the sequence to the next? And our b is our y-intercept, which is our 0 term. So when we go ahead and plug in what we know from here, we know the equation of this is y is equal to 3x plus 15. So if I wanted to know what the 100th term is, I can go ahead and plug in 100 for x, 3 times 100 is 300 plus 15 is 315. So I know that 315 is the 100th term of the sequence, which is a lot faster than writing out all 100 sequences, 100 terms of the sequence. So this is an arithmetic pattern. An arithmetic pattern is adding or subtracting. It does form a line, and we use our equation that we've been using for a line, y equals mx plus b. Now we're going to go ahead and look at geometric. And I always like to think of arithmetic, adding, subtracting. That's kind of the basic, the first thing that you learn when you're learning math. And then we move up a level. And what's harder than adding, subtracting? It's multiplication and division. So when we're looking at geometric sequences, we're looking at multiplying or dividing patterns. Now, the reason why or dividing is really small there is we're never going to write a division anywhere. We always use multiplying. And we know that if we multiply by something like 1/2, multiply by a fraction, or multiply by 0.2, that makes it smaller. So we're actually always going to use a multiplication. However, sometimes it's going to be multiplying by a number between 0 and 1, which effectively makes it smaller, which is just like dividing. So we might recognize it as a dividing pattern, but when we write our formula, we're going to be writing it using our multiplication. So here is a sequence, 7, 21, 63. Once again, our first term is 7, our second term is 21, and our third term is 63. I look for the pattern, and I know that 7 times 3 is 21, and I double check again. 21 times 3 is our next number, 63. Remember, it has to be true for every single one. Now we can go ahead and extend that pattern. 63 times 3 is 189. 189 times 3 is 567, and 567 times 3 is 1701. So let's go ahead and transfer this over to a table. Once again, we always start with 0, although that does not exist in our sequence. And we're going to go ahead and do 1, 2, and 3 once again. Our first term is 7, our second is 21, and our third is 63. We know 7 times 3 is 21. We're going to do the opposite operation of multiplying by 3, which is dividing by 3. And so 7 divided by 3 is 7/3. Now, we can't turn this into a decimal in this case because it's a repeating decimal. It is going to be 0.33333. And so we cannot round that. So we have to leave it as a fraction. However, if it was something like 7/2, which would be 3.5, feel free to write it as a decimal. And I'll let you know when we're doing our Desmos activity and quiz and test whether to write it as a decimal or a fraction. Okay, so we're going to go ahead and work that backwards. That is our 0 figure. Now, our 0 is our y-intercept in this case. Now, this is confusing. Our y-intercept has always been b for a line. However, it changes with our new equation we're about to learn, which is an equation for exponential functions. And that our y-intercept is going to be an a. Stick with me. Now, the pattern in this case is times 3. And the pattern, we don't call it a slope. It's not a slope. Exponentials don't have slopes because slopes are consistent. It is called your multiplier, and your multiplier is your b. So we still only need 2 pieces of information, and they're basically the same, the pattern and the 0. But they're called different things because it's a different type of pattern. So once again, if we're keeping it on this sequence itself, we're just going to work backwards. 7 divided by 3 is 7/3. So once again, you can do the table, you can do the sequence itself. It's whatever is more comfortable and easier for you. So this is exponential. And we know exponential gets really, really big, really, really fast. The very beginning of the year, we did this with the spread of the flu and how that was exponential. Now, this is our equation for all exponential equations. We're actually going to be working on this with sequences this chapter, and we come back for second semester, we're going to really focus on exponential equations even more in all types of things, not just geometric sequences. So in this case, our formula is y equals a times b to the x power. Notice my x is in my exponent spot, which is why it's an exponential equation, and that's why it gets really, really big, really, really fast. Now my a is my y-intercept, which is my 0 figure, and my b is my multiplier, which is my pattern. So we have these 2 pieces of information. We're just going to fill in a and b. Y and x stay the same. So y is equal to 7/3 times 3 to the x power. So 7/3 times 3 to the x power. And this is our geometric equation, which is a pattern that is either multiplying or dividing. Now, we said it with our brain, oh, 7 times 3 is 21, but sometimes it's not that simple and it's not that obvious. And so we are going to take a look at this and use something that's called a multiplier. Now, our multiplier is this very simple formula. It is the next number divided by the previous number. So in this case, we can take any two numbers, 63 divided by 21, and that's going to be a 3, and that's our multiplier or our B. 567 divided by 189 is 3. 1701 divided by 567 is 3. 21 divided by 7 is 3. So whenever you're finding that multiplier, if it's not obvious to you, like, oh, 7 times 3 is 21. If it's not obvious, then you're going to simply very quickly plug it in your calculator. Next number, 21, divided by previous number, 7. And that will give you your B. And then, of course, you use that and do the opposite operation to work backwards in order to find your 0. So our focus today is we're going to be looking at sequences and we're going to determine whether they are arithmetic, adding or subtracting patterns, or geometric, which is multiplying or dividing patterns. And then you're going to go ahead and find the equation, the explicit equation of these patterns in our activity that we're going to work on in Desmos today.